Hello everyone, my name is Amrita Bhatnagar. I am Assistant Professor in CSE Department of AKGEC. Today topic of discussion is Booth algorithm. Okay, so these are the outline which we will discuss in this lecture. Introduction to Booth algorithm. We will understand what is the use of Booth algorithm, why we use Booth algorithm. Then fixed point representation, the number representation, how we will represent a particular number, hardware implementation of Booth algorithm, flowchart for the Booth algorithm, and Booth algorithm examples. So these are all the topics which we will discuss in our lecture. The Booth algorithm is a multiplication algorithm that allow us to multiply the two signed binary integers in 2's complement respectively. The Booth algorithm is a multiplication algorithm which is used for multiply two numbers. It is also used to speed up the performance of multiplication process. It is very efficient too. So we can see here Booth algorithm is used mainly for the multiplication of two numbers. For example, if we want to multiply two numbers plus 4 and minus 1, then this algorithm will be used for multiplication. Now, to understand the multiplication by the help of Booth algorithm, we should know about the fixed point representation, how we can represent a number in fixed point representation. There can be two types of number, positive and negative number. You can see here we have two types of number, positive number and negative number. To represent a positive number, we have a one representation technique which is known as a sign magnitude representation. In the sign magnitude representation technique, what will happen? For example, we want to represent plus 1. Now, for the plus 1, we will take magnitude value here 0, 0, 1, and for plus we will give here 0. It means plus will be represented by 0. So, in the case of sign magnitude representation, we will give magnitude value and sign for the 0 for the plus sign. Okay. So, this is in this way we can represent sign magnitude representation for the positive number. Now, for the negative number. In the case of negative number, we have three representation. First one is sign magnitude, second one is 1's complement representation, and second one is 2's complement representation. Now, what is the different technique for this to represent a number in sign magnitude? In the sign magnitude, for example, if I want to represent minus 1. Now, for the minus 1, we will take 0, 0, 1 for the 001 for the magnitude value, and I will take 1 for the sign bit. So, in the case of sign magnitude representation, we will take minus 1 and sign magnitude 1, we will take one's magnitude value, and for the sign value we will take 1. So, this is the sign magnitude representation. Now, the next representation is 1's complement representation. In the 1's complement representation, we will convert the magnitude value of the number into 1's complement form. You can see here, if the number is minus 1, in the sign magnitude, it will represent like this. But in the case of 1's complement form, it will represent in this way 1, 1, 1. Meaning, I am converting the 0 into 1 and 1 into 0. So, this is the 1's complement form of the number. Sign bit will be remain same, but the magnitude will change. Magnitude value will be changed into 1's complement form. So, this is known as a 1's complement form for the negative number. Now the next representation is 2's complement representation. In the case of 2's complement representation, we will take 2's complement of the magnitude value. You can see example here, -1, 1 for the sign bit, 0, 0, 1 for the magnitude value, then convert into 1's complement, and to convert into 2's complement form, we will add here 1. The value is now 1, 1, 1, and the sign bit will be remain same 1. So the value of -1 here will be 1, 1, 1, 1, 1. This is the 2's complement value. Fine. So because we are using Booth algorithm is also known as a 2's complement multiplication algorithm. We should understand what is the meaning of 2's complement. So we can see here the positive number can be represented only by the one wave which is known as a sign magnitude, but the negative number can be represented by the three different techniques of the representation: sign magnitude, 1's complement, 2's complement. But in the case of Booth algorithm, we will represent negative numbers in the 2's complement form. Okay, that's why it is very important to understand what is the meaning of 2's complement. Every negative number will be represented in the 2's complement form in the Booth algorithm. Now multiplication algorithm in 2's complement representation, which is another name of Booth algorithm, because we are using here 2's complement representation. As in all multiplication algorithms, both algorithm requires examination of the multiplier bits and shifting of the partial product. Prior to the shifting, the multiplicand may be added to the partial product and subtracted from the partial product, or left unchanged according to the following rules. So in the case of Booth algorithm, we will check multiplier bit, because multiplier bit are used for the multiplication. It depends for what step we will follow. It depends on the number multiplier bit. It is 1 or 0. So what are the main rule for the Booth algorithm? The multiplicand is subtracted from the partial product upon encountering the first least significant one in a string of ones in the multiplier. This is the first rule. Second is, the multiplicand is added to the partial product upon encountering the first 0, provided that there was a previous one in a string of zeros in the multiplier. The partial product does not change when the multiplier bit is identical to the previous multiplier. So these are the three main rules for the Booth algorithm. Fine. Now we understand hardware implementation for the Booth algorithm. Now what is the meaning of hardware implementation? Hardware implementation means the hardware required for performing this algorithm. You can see here, this is the diagram for the hardware implementation. In this case, we have two numbers to multiply. First is your multiplicand and another one is your multiplier bits. To store the multiplicand and multiplier, we should have some hardware. So in this case, there is a requirement of two registers for storing the multiplicand and multiplier. You can see here, BR is the register where we can store multiplicand, and there is another register QR which store the multiplier bit, because we have two numbers here. But there is another extra register which is known as a AC register or accumulator register. Now what is the use of this AC register? AC register is used to store the result. When we multiply two number, it can be a big number which cannot store in one register only. So that we should have another additional register which is known as a AC register. In the starting, the value of the AC register will be 0, but after the performing all the algorithm, we will have result in the AC register and QR register. Okay. Now QN. For example, if I have 1010 is a multiplier bit. Okay. So this bit is known as a Qn, because we will start with the multiplication with this bit only, the least significant bit. So, Qn is the least significant bit of the multiplier. Now, next is the Qn plus 1. Qn plus 1 is your flip flop which have value 0 here. Okay. Next is your complementer and parallel adder. What is the use of complementer and parallel adder here? Because we have to perform some complement operation. We have to find out 2's complement form for the negative number, and we have to perform some subtraction operation also there. That's why we required here complementer. And next one is your parallel adder. To add all the numbers after the calculation, we require parallel adder also here. Now, what is the use of this sequence counter? Sequence counter means we have the value. For example, if I have 4 bits as my multiplier, the value of the sequence counter will be 4, because I will perform multiply 4 times in the Booth algorithm. That's why the value of the sequence counter will be 4, and it will decrease every time after the first step, second step and third step on fourth step. And at last, when the sequence counter value will be 0, the algorithm will be stopped, and the result we will get in the accumulator register and QR register. So, this is all the hardware requirement for the Booth algorithm, which is known as a hardware implementation. There is a requirement of 3 registers, complementer and parallel adder, sequence counter, which is another register where we store the number of bits in the multiplier, and there is another flip flop, which is the value of flip flop Qn plus 1 will be 0 in the starting. So, this is the hardware implementation. Now the flow chart or algorithm for the Booth algorithm. You can see here, this is the start button. We will start from here. The value of AC will be 0 here. I have already discussed it. This is the additional register which don't have a value in the starting. That's why the value of AC will be 0 in the starting. Now, next is the Qn plus. The value of Qn plus will be 0 in the starting. Initial value will be 0, and after that, after the changes, it will have some other value also. The next is the N. N is your sequence counter value. If the number of bits n in the multiplier, then the sequence counter value will be n. Multiplier will be stored in the BR register, and multiplicand will be stored in the BR register, and multiplier will be stored in the QR register. Okay. Now the algorithm will start from here. We will check the value of Qn and Qn plus 1. This is the main concept of Booth algorithm. We have to check or examine 2 numbers or 2 bits Qn and Qn plus 1 in our process. If the value of Qn and Qn plus 1 is 0, 1, it means we have to add the value of multiplicand which is stored in the BR into the AC register, and again result will be transferred into the AC register. Okay. Now, if the value of Qn and Qn plus 1 is 1, 0, then multiplicand bits will be subtracted from the accumulator value or AC value. To subtract the value of the BR, we will take 2's complement of the BR and again added it to the AC, and again transferred it to the AC register. Okay. And in the next step, we will done arithmetic shift AC and QR, and then sequence counter will be decreased. And another case is when the Qn and Qn plus 1 is 0, 0 and 1, 1. If the Qn and Qn plus 1 is 0, 0 and 1, 1, it means the value of Qn and Qn plus 1 is same. Then we will not perform any addition and subtraction process in this case. We will directly come to the arithmetic shift right. Okay. And again then the sequence counter will decrease, and we will check the value of the sequence counter. If the value of sequence counter is 0, then the process will end, and if the value of sequence counter is non-zero, then again this process will continue. Now the question is, what is the meaning of arithmetic shift right? Why we use arithmetic shift right? Arithmetic shift right is mainly used for the sign numbers, because in the Booth algorithm we are taking sign numbers, that's why we are using here arithmetic shift right. You can see here in the case of arithmetic shift right, for example, if I have a number, you can see here 1 0 0 1 and I want to shift right here, then what will the next value here? In this case, this one will be lost. We will have 0 here, 1, and in this space we will have again 1, because the previous bit was 1 here, that's why it will be copied here again. So this is the arithmetic right shift. In this case, we will not input 0 from this side. We will insert the bit which is in the most significant bit. In this case, it is having 1, that's why I have copied this value in the first cell also. So this is known as a arithmetic shift right. Now I am taking an example for Booth algorithm. Here we want to multiply two numbers where the multiplicand is your BR 1 0 1 1 1 and the multiplier bit is your 1 0 0 1 1. You can see here this is the negative number because we have 1 in the most significant bit, and again in this case also there is a 1 in most significant bit. That's why these two numbers are negative numbers. Now how will we start our algorithm? In this case we will take AC, where the initial value of the AC is 0 0 0 0, because here we have taking 5-bit registers. QR, the value of QR which have multiplier bits 1 0 0 1 1. Initially the value of Qn plus 1 is 0. Because we have 5-bit register and the multiplier bits are 5 here, that's why the value of the sequence counter will be here 5, 1 0 1, which is 5. Okay, and initially I have find out the 2's complement of the BR register, because we have to add this 2's complement also in the our process, because when we separate the BR value, then we have to take 2's complement and we have to add it is in the accumulator bits. Now we will start. How we will start? We will check the value Qn and Qn plus 1 value. Firstly, we have seen here the Qn plus 1 is 0 and this is your Qn value. Here 1 0 is the value of Qn and Qn plus 1. We have taken here 1 0. 1 0 in our algorithm we have seen that if the value of Qn and Qn plus 1 is 1 0, then we have to subtract the BR value from the AC value. To subtract the BR value, we will take 2's complement of the BR value. So we are taking already taken 2's complement of BR value. So we will add this value to the AC register, and after the adding 0 plus 1 1 0 0 0 0 plus 0 0 0 plus 1 1 and 0 plus 0 is 0. Fine. So in this step we will get 0 1 0 0 1 in the accumulator register. Now what is the next step? Next step is to perform arithmetic shift. To arithmetic shift we will have actually we will perform this arithmetic shift into AC, QR and Qn plus 1. So we will perform arithmetic shift right here. Okay. So when we perform arithmetic shift right, this 0 will be lost. This 0 will be lost and we will get 1 here. Then 1 0 0 1 and this 1 will be come to here, and 0 0 1 0 and last bit is 0, that's why again 0 will be copied here. Okay, so we have performed arithmetic shift. Now I have completed one step of the Booth algorithm. Now decrease the value of sequence counter. Now it is come 4 1 0 0. This step is completed. Now again we will start, because the value of sequence counter is not 0 now. That's why we again continue the process. we can see here, this is the, in the next case we have 1 and 1 in the Qn and Qn plus 1. That's why we have taken 1, 1. And in the case of 1, 1, when we have the both value Qn and Qn plus 1 same, then we will not subtract or add any value in the accumulator. We will directly done arithmetic shift right. So, after the arithmetic shift right, what will happen? This 1 will be lost, this 1 will come to here, 0, 0, 1, 1 and 0 will come here, then 1, 0, 0 or again 0 will be copied here, because the most significant bit was the 0. So, that is why we have taken 0 here. Okay. Now, the next step will be to decrease the sequence counter. Now, the value of sequence counter is 3. Now, I have completed one step also. Again, I will check the value of Qn and Qn plus 1. Now, you can see here the value of Qn and Qn plus 1 is 0, 1. In the case of 0, 1, we will add BR value. So, this is the BR value and we will add this BR value into the AC register. So, you can see here 0 plus 1 is 1, 1 plus 1 is 0 and carry 1, 1 plus 1 0, carry 1, 1 idhar aayega, it will come here and then 1, fine. So, again we will have this value in our AC register. Again the next step is arithmetic shift right. After the arithmetic shift right, what will happen? This 1 will be lost and we will have 0 here. We have 0, 1, 1, 0 and then this 1 here, 0, 0, 1, 1 and again 1 will be copied here in the empty space, because we have most significant bit 1. Okay. Now, the next step, to reduce the sequence counter. Now, the value of sequence counter is 2. Okay. Now, again we will check the value of Qn and Qn plus 1. Now, the value of Qn and Qn plus 1 is 0, 0. So, in the case of 0, 0, we will not add any value in the accumulator. We will directly shift the arithmetic shift the AC and QR and Qn plus 1. So, you can see here this 0 will be lost, this 0 will come here, 1, 1, 0, 1 and this 0 will come here, 0, 1, 1, 1 and 1. 1 will be copied here again. Now, again we will reduce sequence counter value. Now, the sequence counter value is 1 here. Now, again we will check the value of Qn plus and Qn plus 1 and Qn. The value of Qn plus 1 and Qn is 1, 0. In the case of 1, 0, we will subtract BR. Subtract BR from the AC value. So, you can see here the value of BR is 1, 0, 1, 1, 1, 1 and to subtract we are taking 2's complement of BR. So, this is the 2's complement 0, 1, 0, 0, 1 and we will add this value into the accumulator 0 plus 1, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 1, 0, sum, carry 1, 0, 1 plus 1, 0 and there will be 1 carry. In the case of Booth algorithm, we don't have any flip flop to store the carry. That's why we will discard the carry value from here. Okay. Now, the next step is arithmetic shift right. Arithmetic shift right, 0 will lost, 1 will come here, 1, 1, 1, 0, 1, 0, 1 will come here, 1, 1, 0, 0 or again 0 will be copied here. Now, again reduce the value of the sequence counter. Now, it is 0. When we get the value in the sequence counter 0, it means now we have completely performed our multiplication process and the answer will be stored in the these two register AC and QR. You can see here this is a sign value of the result 0, because we have multiplied two negative numbers, that is why we get in the result a positive number, and this is the magnitude value of the result. So, you can check your answer is correct or not by the help of checking the binary value of the number and sign bit also. Now, this is the example of Booth algorithm. Now, I am taking another example also on the Booth algorithm to explain the concept. You can see here, this is another example of Booth algorithm. In this case, we are taking the two values plus 13 and plus 17. We are going to multiply two values plus 13 and plus 17 here. So, we are, and this is multiplicand is our plus 13 and multiplier is plus 17. That is why plus 13 is stored in the BR and multiplier is stored, which is 17, is stored in the QR. And we have taken 2's complement of the 13 also. So, this is the 2's complement of 13 value also here. Now, you can see here the starting value of AC is 0. This is the 6-bit register here. Now, we have taken example of 6-bit Booth algorithm multiplication. So that we have 6-bit register here. So, then initially the value of AC or A register is 0, 0, 0, 0, 0. And in the QR, the value of multiplier will be stored 0, 1, 0, 0, 0, 1. And the starting value or initial value of Qn plus 1 will be 0. And the sequence counter value will be here 0, 1, 1, 0, which is equal to 6. Now, we will start our algorithm. We will start with checking the value of Qn and Qn plus 1. In the starting, the value of the Qn and Qn plus 1 is 1, 0. So, first step will be start with the subtraction of the value from the A to A minus B. So, B, the 2's complement, I have taken 2's complement of the BR register or B register. So, then we will add this value into the accumulator. After the addition, we will get 1, 1, 0, 0, 1, 1. And the value of the QR register is 0, 1, 0, 0, 1. And the Qn plus 1, 0. Now, we will perform arithmetic shift operation. In the case of arithmetic shift operation, 0 will be lost. 1 will come here, 0, 0, 0, 1, 0, 1. This 1 will come here, and 1, 0, 0, 1, 1, and in the last place we will have 1 again, because the most significant bit was 1 and we are performing arithmetic shift, right? That's why we will have 1 here also. Now, the last step is reduce the sequence counter. Now, the value of sequence counter is 5. We have completed one step. Now, next in the next case, again we will check the value of Qn and Qn plus 1. You can see here the value of Qn and Qn plus 1 is 0, 1. This is 0 and 1. So, then in the case of 0, 1, we will add the value of B. In the accumulator, the value of B is 0, 0, 1, 1, 0, 1. We will add these two values. 1 plus 1 is 0, 1, carry 1, 0 plus 1, 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1. And the carry bit will be discarded here. Fine. Now, next step is arithmetic shift right. In the case of arithmetic shift right, when we perform, 1 will lost, 0 will come here, 0, 0, 1, 0, 1, and this 0 will come here, 1, 1, 0, 0, and the last bit we will have 0 value, because the most significant bit was 0. That's why we have copied this bit into this place. Now, the next step is to reduce the sequence counter value again. Now, the sequence counter value is 4. Now, again we will check the value of Qn and Qn plus 1. Now, the value of Qn and Qn plus 1 is 0, 0. In the case of 0, 0, we will not add or subtract any value in the accumulator or AC register. Then we will perform arithmetic shift right. Arithmetic shift right, 0 will lost. We will have this 0 here, 0, 1, 0, 1, 0, 1 will be here. Then 1, 0, 0, 0, 0, and again we will have 0 value here. Again, next step is we will reduce sequence counter. Now, the sequence counter value is 3. Now, again we will check the value of Qn, Qn plus 1. You can see here again the value of Qn and Qn plus 1 is 0, 0. In the case of 0, 0, we will not add or subtract any value. What we will do here? Arithmetic shift right. In the arithmetic shift right, this 0 will lost. This 0 will come here. 1, 0, 1, 0, 1, and this 1 will become here, and we will get here 0, 0, 0, 0 and 1 0 here, because last bit was 0. Now, next step is to reduce the value of sequence counter. Now, the value of sequence counter is 0, 1, 0. Now, again we will check the value of Qn and Qn plus 1, which is 1, 0. In the case of 1, 0, we will subtract the value of B. In this case, the value of B is 0, 1, 1, 0, 1, and the complement of 0, 0, 1, 1, 0, 1 is 1, 1, 0, 0, 1, 1, 1. Then we will add this value and we will get 1, 1, 0, 0, 1, 1. Now, we will perform arithmetic shift right. In the case of arithmetic shift right, this 0 will lost, 1 will come here, 0, 1, 0, 1, 1, 1, and this 1 will come from here, 1, 0, 0, 1, 1, and this 1 will come here, because the last bit was 1. Now, the next step is to reduce the sequence counter. Now, the value of sequence counter is 0, 0, 1. Again, we will perform one step for the Booth algorithm. Then we will check the value of Qn and Qn plus 1. The value of Qn and Qn plus 1 is 0, 1. So, we will add the value of B here. So, the value of B is 0, 0, 1, 1, 0, 1. We will add these values. 1 plus 1 is 0. Carry bit is 1. 1 we will having 1 here. 0 plus 1 is 1. 1 plus 1, 0. Sum carry 1, 0, carry 1 and 0, and again we will have 1 carry bit which is discarded. Now, we will perform arithmetic shift right. In the case of arithmetic shift right, we will lose this 1, 0 will come here, 1, 0, 1, 1, 1, and this 0 will come here, and 1, 1, 1, 0, 0, 0, and in the last bit we will have 0. Fine. Then again reduce the value of sequence counter. Now, we will get the value of sequence counter 0, 0, 0. It means we have performed all the steps of our multiplication process. Now, the result is stored in the AC register and QR register. You can see here the sign bit of the result is again 0, because we have both positive numbers, that's why result is also positive. If we have both negative number, then result will be positive. But if we have one number is negative, number is positive, then we will have negative result. And we can check our magnitude value in from these two registers. So, we will get 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, which is equivalent to plus 2, 2, 1, which is in the decimal value. So, our result is correct here. So, in this way, we can perform our Booth algorithm, and we can find out the values of result in the AC and QR register. Okay. So, we have taken these two examples. I think you will understand it very easily, and you can perform this Booth algorithm very easily. Thank you.